Greetings, friends. This is Radio Geek Garage once again. In the previous video, we discussed how to match antennas with cables, and for the most common cable, we used a 75 ohm cable. But have you ever wondered why the cable's impedance is 75 ohms? To understand this, let's revisit the principles of a quarter-wave vibrator. When a signal is applied to a rod antenna, with a quarter-wavelength signal matching the length of the antenna, a standing wave is formed in the antenna with a potential maximum at the open end and a current maximum at the connected or grounded end. In the early days of radio engineering, it was believed that the standing wave in a quarter-wave vibrator would tend to be ideal. That is, at the current maximum, the voltage tends towards zero, and since the wave impedance is the ratio of the voltage to the current, the impedance of a working quarter-wave vibrator should tend to zero. Therefore, the rod antenna at the current maximum should be connected with a cable whose impedance tends to zero. However, during that time, there lived and worked an outstanding figure named Heinrich Rudolf Hertz, the very person after whom the unit of frequency is named, the one who created the half-wave dipole and derived key formulas in radio engineering. He looked at the situation and said, "Wait a minute, something's wrong here. We can't have an ideal standing wave in a quarter-wave segment, at least because the antenna radiates part of the energy, meaning the reflected wave from the end of the antenna will always be smaller than the incident wave." Hertz conducted numerous experiments with many of his antennas and dipoles. The discovery he made shocked the world of radio engineering. It turns out that no matter which antenna he used, and no matter the impedance of the antenna's element, at its resonance frequency, whether high or low, the antenna radiates as much electromagnetic power as a 73 ohm resistor radiates in thermal power. This value was called the radiation resistance. Its value was verified by other radio engineers, and it was decided that cables should be made with 75 ohm impedance. However, it was soon discovered that only the dipole has a radiation resistance of 73 ohms. Antennas of other shapes have different radiation resistances. For example, a loop vibrator has an impedance exactly 4 times greater. This is when methods for impedance matching began to be explored. A very important conclusion drawn from these experiments is that the impedance of a working antenna does not depend on the wave impedance of its element. But does this mean we can completely forget about the wave impedance of antennas? It turns out no. If a dipole works as part of a more complex antenna system, its wave impedance plays an important role. For example, the Nadonenko dipole is often used not as an independent radiator but in combination with a matched symmetric line. For instance, one quarter wavelength may correspond to the dipole, and the remaining quarter wavelength corresponds to the symmetric line. Such an antenna system can operate at a frequency twice as low as the dipole's frequency. In this case, matching the wave impedances is crucial because the dipole is connected to the line at a point other than the current maximum. In principle, for ideal matching between the cable and the antenna system, the wave impedance of the cable should match both the radiation resistance and the wave impedance of the antenna element. Furthermore, there are antennas where reflected and standing waves do not exist by definition. These are traveling wave antennas. In this case, the cable's wave impedance should only be matched to the wave impedance of the antenna element. This can be done using ferrite matching transformers or matching devices with smoothly varying wave impedance. Let's summarize. The input impedance of any dipole and quarter wave segment working at its resonance frequency is 73 ohms. Radiation resistance does not depend on the wave impedance of the antenna element, but it does depend on the antenna's shape. In complex antenna systems, the wave impedance of the cable, the wave impedance of the radiator's element, and the radiation resistance of the antenna system should be matched. For traveling wave antennas, it is only necessary to match the wave impedance of the element with the cable's wave impedance. If this video was helpful to you, please like, share with friends, and leave comments about topics you'd like to see discussed. Good luck, and see you in the next videos.